Okay. Hi everyone, I'm Alberto Modesti and I'm in my second PhD here with a thesis about a three-dimensional model and simulator of energetic plumes from space plasma thrusters under the supervision of Eduardo Edo, Jiewei Zhou and Filippo Cichocki, which is the creator of the code I'm improving. In my second PhD year, I will recap a little the motivation and goals of my thesis, which are the improvement of the 3D simulator of plasma thruster plumes, especially with what concerns the electron fluid models. This simulator has to be capable of representing well the object interaction and the electric circuit behavior in order to be able to simulate the free space and ground facility conditions. So many ancillary models are needed for better consistency of the simulations. The goals, the outputs of this thesis will be a code which is flexible, so that can simulate different kind of thrusters, scenarios, and also boundary conditions. The code has to be able also to interface easily with other types of the codes of our research group. The main goal is to use it for preliminary design for experimental support, for example, in the frame of projects. The methodology I'm using involves independent improvements, both in the modeling of the physics and numerical algorithms. These models will be validated through test cases already existing in the code, comparison with previous models, and also comparison against other codes. Also, by supporting several projects involving university and companies, we have the opportunity to apply the code in challenging scenario and with the full capabilities of the simulator. Finally, experimental validation against prototypes is foreseen, and it's useful to have companies working in the project we are involved. The code I'm using is a 3D hybrid particle-in-cell fluid code called EP2+, and it was already mentioned by Matteo in its 2D version, but the original one is 3D, and it's hybrid because it models the heavy particles such as ions and neutrals with a particle-in-cell model in which the motions of the particles, the collisions and surface interactions are modeled. Then there is a code module responsible for the object interaction, so taking into account the existence of 3D object material surfaces internal to the domain with specific electrical properties, so to better model the interaction of the plasma with the wall and with the object that could have some electrical properties. Then the electron fluid part of the code solves the continuity and the momentum equations, retrieving then the electric and electron current densities, and closing the model with the thermodynamics that can be a simple polytropic closure so far, or as it is being improved now with the inclusion of energy equation. An additional module is responsible to compute the density and the potential maps in non-neutral zones, so taking into account the zone in which the plasma quasi-neutrality assumption fails, and the model closes with the retrieving of a self-consistent electric field from the electric potential. In order to recap, to summarize my first year, last achievement was the implementation of a new numerical discretization scheme for the momentum and continuity equations, which were previously solved with a full finite difference discretization, which is affected by the truncation error that usually appears, especially with the coarse meshes, as an artificial source of electric current. This electric current perturbs the solution and rises on the point in which we don't solve the momentum law, and we apply the Dirichlet condition for the potential. This kind of artificial current can be mitigated by adopting a high resolution mesh, whose consequence is to increase the simulation times and the computational burden. The new scheme is finite volume 1, So the discretization on a staggered scheme, on a staggered mesh. So the scheme is conservative and it's able to detect even small currents. I'll explain later why it is important, and doesn't make artificial currents to rise. I started my second year of PhD by validating this with this new staggered method against the previous finite difference scheme, which at medium high resolution is not so much affected by the artificial current error. And these two schemes coincide, so the new scheme was basically validated against the previous one. And we started improving the boundary condition in order to be able to put 3D objects such as solar arrays, spacecraft assembly, or cathodes. And we tested the scheme both in a high-on thruster scenario and in a Hall effect Trustel-Bloom scenario. Having already simulation with the previous scheme, we were able to validate the new one and be sure that it works as expected. Lastly, we applied it to a magnetic nozzle scenario for which we wrote a paper, and we saw that there's a good agreement with the experimental density, current, and ion velocity distribution function. So the new scheme was working fine. And going into the core of my second year, that involves the European Horizon 2020 projects, Aspire and Cheops, we wanted to improve further the capabilities of the code and the complexity of the simulation by adding also ancillary models, non-neutral solver, and different kind of surfaces and 3D objects inside the domain. The purpose of this simulation were to replicate the experimental conditions in which the thrusters were tested. So in vacuum facility conditions, we have a metallic chamber with pumps and with a background density which is responsible to different effects with respect to the ones happening in the free space. So the simulations we were setting up in order to simulate these kind of thrusters working in the vacuum chambers feature 3D thruster object, chamber with at the boundaries, so a domain as big as the vacuum chamber employed, with the free loss downstream pumps resembling the cryo pumps working for the pumping, and an equivalent circuit model in order to model better the plasma object interaction and the collected current by the thruster case assembly. You can see the mesh on the top right with the 3D thruster object and the downstream pumps on the right. And the electric circuit modeling was important in this phase because the experiment employed a direct drive method which tuned the thruster case potential with respect to the plasma in order to collect more or less stray current from the plasma. Their objective was to collect zero current because that's the purpose of not charging the spacecraft and the thruster in space. And we were able to formulate a model which was able to replicate this kind of behavior. The preliminary simulation were also to assess the dimension of the downstream pump surfaces in order to reach at steady state with the mass flow injected by the thruster, the topology and values of the density and pressure in the vacuum chamber. So we tuned the surface area of the pumps until we matched the experimental pressure and density, and we used this condition as initial starting point for the plasma simulations. The main outputs of these simulations were the behavior of the stray current collected by the thruster case assembly, which is metallic. And you can see here, for example, you can see the ion and electron current density topologies. You can see that the ions are following the expansion of the bloom, and some of them are turning back towards the back of the chamber. A fraction of these ones are also collected by the thruster case, and they are responsible for the positive part of the electric current collected. The electron ones instead have a more complex topology because they are magnetized, and the topology employed in these experiments was a magnetically shielded one. And these electrons are more sensitive to the thruster case potential. Indeed, you can see the comparison in the bottom plots between the experimental behavior of the stray current collected by the thruster case and the numerically founded one. They match in terms of behavior and trend, even if the values are different because of the closure employed here, which is a polytropic. And we can see that apart when the thruster case potential when the plasma potential is very positive with respect to the thruster case, so the thruster case is very negative, the electron collected are almost none, so the curve becomes almost flat. And instead, when the thruster case potential and the plasma one are comparable, the thruster case starts to see the thermal flux of electrons and behaves like a plasma probe. This was a first assessment of the capabilities of the code, both with the solving, taking into account the non-neutral zones take place at the back part of the chamber, with the electric circuit capabilities and the metallic components which are charging with respect to the plasma or keeping a fixed input potential. Finally, in these weeks, I started a new, the implementation of the energy equation as a better closure for the electron model that previously adopted a polytropic closure which only follows the density profile of the electrons and doesn't take into account the collisions process or the losses of energy due to the diffusion across the magnetic field and the anisotropicity due to the latter. So this equation is instead introduce these effects, and you can see from these first results that the polytropic one only gives a profile of the temperature that follows the expansion of the plume, so the density of the plume. Instead, the energy equation in this is a extreme case in which we put an axial magnetic field along the vertical direction, and we close the equation with a pure Fourier law. So we only have the diffusion across the magnetic field lines, and the cooling happens in those directions. So to close the problem with this kind of equation drastically changes the output of the simulation. So in order to summarize the second year achievement, they follow the logic of first validation of the new scheme and improving of it with more flexibility, testing it with the new thruster and boundary condition scenario, and compare it with the previous scheme to validate it. So we have a suite of test cases in order to be sure that it's working well. Then the application, which is the core, the application of the new scheme and all the other ancillary models for simulating the experimental conditions for the two projects involved, and the new improvement of the fluid electron equation with the formulation of the energy balance and heat flux equations. The scientific production for this second year were some contributions to conferences, one journal paper, and a project deliverable for one of the two projects involved. And finally, the next task will follow the same logic of the ones which I started the year with. So improving the boundary condition flexibility and the scenario for the energy equation and with the new scheme as it was done for the momentum and continuity equations. Adding 3D object, simulating more thruster conditions, and coupling with hyphen code, which is a 2D simulator of a near plume and discharge chamber for these thrusters in order to improve the input condition. Also, we plan to improve the setups and simulation of the head thruster of the project with the new upgraded fluid model with the energy equation, and some other improvements feature the inclusion of new circuit elements and properties, better interface with other code, and improve the meshes both for large plume simulation and vacuum chamber. And lastly, a 2D version of the code is foreseen because this new scheme was not translated into 2D yet, which is the version of EP2+ with Matteo is working with. So we are coupled in this way. Thank you. I list here the project involved in this thesis, and if you have any question, feel free to ask.